In our previous video, we used the automatic pipe sizing feature to size our pipes by forcing a flow out of each offtake in the system. Next, we'll unconstrain the model and use flow controllers or other resistance components to control the flow distribution. Let's revert to our original modeling approach, where we used a known flow node at the inlet to supply the system. Let's set the inlet flow to 50 cubic meters per hour into the network. At each boundary, we'll use known pressure nodes. To simulate resistance at the offtakes, we'll set the pressure at these nodes to 1.2 atmospheres. We'll also display the flow at each outlet. Now, if we recalculate, we can see that the flow distribution is improved due to changes in pipe sizing in the header. However, we're still not achieving the required 10 cubic meters per hour through each offtake. To achieve this, further analysis of the pipe sizes might be necessary, but it's highly unlikely to succeed using standard pipes. Instead, we can use flow controllers to manage the flow distribution. Flow controllers are available in the Controllers tab of the component palette. These allow us to specify a design flow for each pipe. FluidFlow then calculates the required valve opening to achieve that flow. Let's place a flow controller on each offtake. You'll notice a red dot appear on one side of the controller. This indicates the flow direction. The red dot represents the discharge side of the valve, which can be set in the input editor by clicking the three-dot button for the valve and cycling through the available pipes. With the flow direction set, we'll select a suitable valve size from the database. For this example, I'll choose a 1.5-inch valve, which is one size smaller than the pipe size. After placing controllers on each offtake, we now have another example of an over-constrained model. In this setup, both the total inflow at the boundary and the individual flows at each offtake are specified, while they mathematically balance, such that total inflow equals total outflow. This type of constraint results in convergence issues. When we press Calculate, you will see we get a large number of iterations, significant warnings, and the system produces unreliable results. To resolve this, we simply remove one of the controllers. The required flow will still be delivered as a balance of the specified inflow. When we recalculate, the system converges quickly with no errors. The valve openings are around 50 to 60%, delivering the desired flow to each offtake. While flow control valves are an effective solution, they're also the most expensive option, requiring additional cabling and instrumentation. An alternative is to use manual valves for balancing the system. For example, let's replace one flow controller with a globe valve and set it to 50% open. After recalculating, we see that the flow through this leg exceeds the requirement. By trial and error, we can throttle the valve until we achieve the required flow. At 34% open, the valve delivers exactly 10 cubic meters per hour. Another option is to use an Orifice plate. This is a cost-effective solution for systems where precise flow control isn't necessary. Let's change this controller with a thick Orifice plate. Instead of relying on trial and error to determine the orifice diameter, we can use the autosize feature to speed up the process. By engaging the autosize and specifying a design flow of 10 cubic meters per hour, we can obtain an orifice diameter of 29 millimeters. Once we have this value, we'll turn off the autosize feature and manually input the determined size. Now, we get the required flow of 10 cubic meters per hour. In the next step, we'll explore using the autosize feature to determine a pump's duty point within the system.